Hello, it's my pleasure to talk to
Okay, so it's 1:15. I was gonna get us started again. So this is the session on GPUizing code, or I guess compilerable code. I know that Sam Rabin is on the unit testing Google Meet and is giving his like 1 hour spiel about PyTest and NPF unit. Our first talk was pre-recorded, so I think what I need to do is mute the audio in the room so you don't get an echo. Then I'll hit play, and then if people online, it's like give a thumbs up if you can hear the audio, or a thumbs down if you can't, and we'll play with it if it doesn't work. But I think that will work. So the first talk was from Wei-Kun Zhang, who's at the Berkeley lab and is one of the Amrex developers.
Hello, it's my pleasure to talk to you about AMX, which is a performance portable software framework for adaptive mesh refinement applications. First, let me give you a brief overview of AMRX. So AMX is we call it a software framework. So a lot of application code use AMX to build their code, and it provides a lot of features. And you can see a list here. But today, I'm mostly going to talk about the performance portability layer. What that means is you write, the same code that can run on CPU and all kinds of GPUs. So let me first talk a little bit about the history of AMX. So AMX started as a co-design center project in DOE's Xscale Computing Project, ECP. So we started in 2016. And now the ECP has ended, but we're still, continue the development of AMX. And during the ECP project, there are 6 other ECP application projects that they use AMX as their building block. And AMX is based on Boxlight. That's the name of the code before AMX. And at the beginning, we used C++11, and actually almost all our computational kernels functions are in Fortran. So we mix C++11 and Fortran. And then later we switched to C++14, and now it's C++17, and mainly because of the need for GPU programming. And we started as like a pure CPU code, but now it's like a performance portable, so it can run on different kinds of GPUs. And we have added a lot of more features, and the code is fully open source. And now it has become a project of the Linux Foundation. So here the sampling of AMX application code. And I'm not going to talk in detail because we don't have time. But I'm going to highlight just one application, which is the WarpX code. And it won the Gordon Bell Award a few years ago. And you can see the code runs on several supercomputers. Frontier, that's AMD GPU machine, Fugaku. It used to be #1. It's a CPU machine in Japan, and the Summit and the Perlmutter are NVIDIA GPUs. And okay, so now I'm going to focus on the performance portability. But before I do that, I actually want to mention, even though the AMR is in our name, and a lot of our code do use AMR, but we also have code that do not actually use AMR, So, so the performance portability layer, what we have is something we build using vendors C++ programming models. For NVIDIA GPUs, we use CUDA. For AMD GPUs, we use HIP. For Intel, we use SYCL. And this was a decision we made in early 2018. So we tried a number of options, and we decided that that's was the best way to move forward. And there are certain advantages, and especially I think the most important thing is the vendor C++ solutions are much more mature and stable than other options like OpenACC, OpenMP, or Fortran. And here I show you two figures. Those are taken from a survey paper. It surveys the application code in the ECP project. And you can see most of the code use C or C++. There's some Fortran code, and they actually later switched to C++. And there are basically four categories of how they do their GPU programming. And some of them use the native GPU, which means they write CUDA for NVIDIA GPUs, HIP for AMD GPUs. And some use loop pragma, basically means OpenACC, OpenMP, and some use Cocos or Raja. Those are the two performance portability, software. And some use the co-design side project or library, like AMX. There are 10 ECP codes use AMX. So things I'm going to talk about some details of AMX. So I'm going to show you an example of this is the AMX grid. So you can see the three levels: level 0, level 1, and level 2. And you have higher resolution at the higher refinement level. And so a basic class we use is called a box. So that represents a rectangular domain in the a global integer index space. And we also have the concept called the integer vector. That's kind of like in 3D space, it's IJK. It's kind of like integer tuple, represent where you are in space. And we have different index types. It might be cell-centered or nodal or phase, that type of thing. And a very important data container we use is called multifab. It stands for like multiple Fortran array box. And because it's basically multiple, you think it as multiple Fortran arrays. And from the picture, you can see, for example, we might have grids like this. So each box is a Fortran array. We use a Fortran array to store the data, but here we have multiple. And it's a distributed data container that handles, MPI communications. If you, call, say, I want to do a GOSA exchange, it can do it for you. And I want to emphasize is, by default now, if we build for GPU, the multifab will put the data in GPU memory. But if you want, you can also say, oh, I want to put the data in CPU memory. You can also do that. For example, here you can say it's CPU arena. And as I just mentioned, a multifab contains multiple F3 boxes. F3 box is a container for like a multi-dimensional array, and typically it's a 3 spatial dimension plus 1 extra one for the number component, like x velocity, y velocity. And we also have a class called array4. That's a lightweight class that you can use that on GPUs. And let's look at a very simple example. So here I have a Fortran 3-dimensional loop. right? So given B, I just compute some. There's a formula can use to compute A, right? Um, so how do we do this on GPU? Well, in MX, what we do is, this red block of code shows you how to do it in MX. So we have a function called a parallel for, and it takes actually just two arguments. One is box that tells you the iteration range. So we build a box. You say this is my lower loop bound. This is a higher loop bound, right? And the second thing is the lambda function. It's a C++ construct called lambda function. And you see that the important thing is the loop body is almost identical, except there's an extra. Oh, sorry. Yeah. So the function code, you don't need a semicolon. But yeah, for C++ code, it's just one extra semicolon. And let me show you some details how we actually implement those things. So here show you even in simple example, it's a 1D loop. So if it's a CPU code, you might have a 1D loop like this. And if you write in CUDA, you might do something like this. And you see, but in MX, what you do is you launch a parallel for function to do that. And what happens is internally, we have something like this, not exactly like this, but just for illustration. So we have a parallel for function will launch a GPU kernel for you, and it will call the function you passed in as argument. And for 3D loops, and it's similar. For example, this is a 3D loop, and then you do something like this, and internally we have to do this type of things. You have like, we launch a GPU kernel. It's kind of like 1D indexing. We convert to like 3D IJK, and we do all those things for you so that you just write a function like this. We also provide support for reduction on GPUs. And here is an example. And in this example, we actually do two types of reductions. First, we do a reductions, do a sum on some double precision numbers, and also compute the max of some integer data. And here is another example of you can provide a custom data type for reduction. And I want to note that no atomics is needed because the atomics is typically slow in GPUs. You want to avoid it. And we also provide the so-called scan. There are other names, prefix sum or partial sum. It's important for a lot of MX applications. And we also have the capability to do kernel fusion. So for example, here the example, we may have like a loop over a parallel for function. So each parallel function is a kernel, but loop might have like 100 iterations. So you launch 100 small kernels, it's going to be very expensive. So we have a way to do that is, you say, I have those things I need to do. You push that into a vector of tags, and then we just launch a single kernel to do all those work, and it's much faster. And we also have ways to optimize the runtime parameters. The thing is, for example, in a lot of code, in the innermost loop, you may have like branches. If there's a runtime option this, I do this. If other do that, sometimes it's quite complicated. In this example, I have 4 possibilities for option A, 2 possibilities for option B, and you have like 8 combinations. And if you really want to write optimized code, you want to move those branches outside the computational loop. But then you end up with really long code and also a lot of code duplication. So you have your if statement outside. But we provide a way to automatically do those optimization for you. And so now let me talk a little bit about memory arena. This is actually very important because if you use CUDA, the CUDA malloc is actually quite expensive. So if you CUDA malloc, CUDA free, and then later you have to malloc again, it costs a lot of time. And so we provided our own heap allocator that do the memory allocation for you, and to make things faster. And we also have a important arena. We call it async arena. The reason for that is that the GPU kernels are asynchronous with respect to the host. So for example, in this example, we have a F3 box that's like a Fortune array, and then we launch a GPU kernel to use that array. And if without that synchronization line, the code has a bug because the GPU kernel is actually still running on GPU, and then on the CPU side, we're going to delete the memory. So it's going to be a bug. But what we do is they say, oh, we make it, put the array in asynchronous safe memory arena. And then, not only it's safe, but also it's faster. So the lessons that we learned is that the performance portability layer is actually, it's crucial to a lot of, success. And also it's important for us is the interaction with the application teams and with the GPU vendors and our online users. Okay, this is my last slide. So AMX is an open source project. So we have a lot of GitHub contributors, and your contributions are welcome. And we have an AMX Slack channel. So if you want to join, you can email me, and we have our users group meeting now annually. Okay, so I'm going to stop here. If you have any questions, please feel free to email me. Here is my email. That's it. Thank you.
Of course.
We'll let them know.
We can record our clapping.
Excellent recording.
Okay, so Andrew, you want to use your?
Yeah.
Are you using already? You go in. Did you have the link?
Can I just say? Do you want me to send it to you, Daniel?
Okay.
Hi everyone, my name is Daniel Abji. Today I'll be presenting about our effort to compare two different adaptive mesh refinement techniques for numerical result prediction. Both are capable of running on the GPU, which is at the focus of my presentation today. Here are my collaborators. Anna Nugrin is from the Lawrence Livermore National Laboratory. The AMRX, she's an AMRX developer, lead developer. I'm Gerald Lewis from Naval Postgraduate School, and Isidro is from GSL. So why do we want to do AMR on the GPUs? So we could keep on using uniform grid resolution. For example, MPAS is trying to develop a 1 kilometer resolution, but that's too expensive. And we just want to refine the regions that we're interested in. For example, we would like to be able to track tropical cyclones or some convective activity. So we could just refine that domain, and this typically consists of like 1% of the domain. So it's a wasted effort to use uniform grid resolution. So GPUs give us like an opportunity to take advantage of the massive compute available. But MR codes, adaptive mesh refinement codes, are typically not regular or easily parallelizable. So that's a major challenge. And the question we want to answer is, can we map AMR effectively to many core architectures, including GPU, laser, others? So the two approaches we will investigate is the first one is called the level-based AMR. This is the older approach and typically what you probably heard of as adaptive mesh refinement. There's also the other approach, the tree-based AMR. So in the second approach, we do refinement element-wise. For 2D refinement, that would be like each cell would be divided into 4 quads, and for 3D, that would be like 8 cubes. In the case of level-based AMR, this maps really well to the GPU architecture because you still have uniform grid. So you can still keep on thinking about your code as if it was using your rectangular grid, and you have a number of rectangular patches that overlap on top of one another, while the tree-based AMR still has like a single grid with different refinement conducted on top of it. So it's kind of difficult to manage the tree-based AMR, particularly on GPUs. But there are also existing libraries like pForest. There is also a counterpart for that for P6 that can be used like on spherical geometry, where you typically want to refine in the horizontal and keep the vertical refinement the same. So there are libraries, and the MRX framework that the previous speaker talked about is used in the level-based MR approach. And this we concluded that the level-based MR is more suitable for GPUs, but both approach could be ported to the GPU just fine. Here I'm showing a diagram. So then on the left, that's the level-based approach. You have 3 levels, and the refinement is done like twice refinement in every level. We have 3 levels. The red one is the higher level. So when you do that kind of refinement, you have to also think of the time steps. So the time step is also, every time you refine, you decrease the time step by 2 times as well. On the right, we have the Nebula SCM code that we used for the tree-based approach. This is just one grid, but you could still have like 3 levels. Unfortunately, we couldn't come up with a single code that does both of them because managing mesh is very complicated. So the right one, the tree-based, is using the high-order discontinuous Galerkin discretization. That's why you see the grid is slightly different, while the left one is using finite difference, which WRF is based upon. So ERF is basically WRF rewritten in C++ and using the MRX framework. I have done previously work on porting WRF to the GPU, and that's as you all are familiar with, written in Fortran. It's difficult to use an advanced library like MRX in WRF directly. So I believe that's one of the reasons why they rewrote WRF in C++. They call it the Energy Research Framework, ERF, and this uses the MRX framework. Nebula SCM, this is in-house using high-order discretization and tree-based MR, and we compare these two using several benchmarks, standard benchmarks like the rising thermal bubble, transport on the sphere, and acoustic waves. Here I'm showing, by the way, this slide is created by an AI, so this is an AI in this presentation. I really like that the picture anyway here. It's demonstrating that ERF is using block-structured mesh refinement, while the tree-based is kind of messy. So each cell, whenever it's refined and coarsened, you have to keep that information later on. Like if you want to coarsen the mesh, you use a tree you stored on disk or in RAM to do that. So irregularity is the main challenge. So that's why we believe that the level-based approach is more suitable for GPUs. But the bottom line is the mesh management itself has to be conducted on the GPU. Like if you think of doing that on the CPU, because MR codes are typically very complicated, that's going to dwarf you compute kernels, and you're going to lose on performance. So it's best to keep the mesh management code also on the GPU. That's a common lesson for both approaches. AMRX is it uses hierarchical parallelism. You could do MPI and then offload to GPUs using CUDA or heap or SQL or whatever you want. And also you could do the same on the CPU as well. Load balancing is critical. So whether you use the path-based or the the tree-based approach, you have to use advanced algorithms like space-filling curves or knapsack algorithm to load balance whenever you do AMR. So this has to be done technically, like every time step if you want to refine every time step, you have to do load balancing every time step. So this is quite intensive, and the design goal is to have that in a library so that you can just plug it in your numerical simulation code, and you can focus on the physics, the other stuff. Here I'm showing two simulations: the rising thermal double simulation on the left using the tree-based approach, on the right the level-based approach. As you can see, both are doing well. You can see the refined grid in the background. I think both are using two levels of refinement here and here, and they perform reasonably well, and they can track dynamic features, which is the goal of this project, equally well. Here I'm showing an animation using a rather conservative regrading approach. It's a very wide, but you can try and fit in the feature as closely as possible by changing the AMR parameters. Here I'm showing the same thing done on the sphere. Unfortunately, AMR is not capable of, at least up to last year, it's not capable of adaptive mesh refinement on the sphere that we need, for global simulations. So this is done by the Nebula ASM. So one challenge we observed is that one issue is mass conservation in AMR is fundamental, because in the level-based approach, you're transferring solution from the coastal grid to the final grid, and you typically lose some, it's very hard to conserve mass with that kind of approach. But since the tree-based approach is based on a single grid, even though it has different refinement, it should be able to conserve mass equally well as a uniform grid. What is the AMR payoff? So comparing uniform grid resolution versus AMR for the 2D RRTB test case, we found out about 6 times performance improvement. So there is that payoff. We also did some weak scaling tests on Hera, using up to 512 GPUs using the ERF code, and we found it to be scaling pretty well up to 512 GPUs and 1,000 CPUs. Typically, you lose that performance when you go from 1 node to 2 nodes. The internode latency, drops your performance, but after that, it's more or less. I can't say constant, but it's much better afterwards, and we find up to 70% scaling efficiency on here. In terms of speed up, comparing one P100 is a very old generation GPU versus one Haswell CPU, we found out 10x speed up. So using AMRX, you get scalability, extreme scalability, up to millions of GPUs. I did only 512 GPUs, but the previous presentation I think showed scalability up to several thousand GPUs. You get speed up, GPU speed up, and we found out that to be the case, 10 times speed up comparing single GPU versus single CPU. And also you get AMR, which is not commonly used in many courses. WRF has nesting capability. We know that, but other than that, I haven't seen AMR being used. So you get 3 things using the AMRX library. So what are the lessons we learned from using AMRX? So I presented the Nebula ASM just as something you should not be doing. So I initially that's an in-house code and we wanted to implement AMR ourselves, but that's not the approach I recommend. So use something like AMRX that gives you a lot of advantage. Workload density is important. So in the previous week scaling figure, I think when you use small workloads, your GPU performance is going to tank. So make sure that you have enough work per GPU. Do everything on the GPU, like if you like in case of level based, when you do coarse to fine or fine to coarse solution transfers, you have to do it on the GPU. Like if you do something on the CPU, then that's not going to help. So final conclusions, practicality, I recommend AMRX. You can get speed ups up to an order of magnitude. And also there is a time saving that comes from AMR. Thank you.
We have time for 1 or 2 questions if there are any. If not, I can sit up for that. Thank you.
While you're setting up, I guess did you have to change your solvers in any way to get them to run more efficiently on the GPUs?
The solvers remain the same.
So you just code to code pretty much.
Yeah, particularly for the layer-based approach, each patch would be using the same code because it's rectangular grid. And
Oh, okay.
for the tree-based, you may have to make some issues.
Thank you.
Okay, so our next speaker is Ren Stengel from here at NCAR.
Hi, everyone. I'm just going to really briefly apologize for the fact that I'm getting over a cold. So if you can't hear me, let me know, and I'm happy to try to speak up a little bit more loudly. But today I'm talking about developing language interoperable atmospheric modeling software, an approach for integrating CAM Fortran parameterizations into E3SM C++ code. So there have been multiple ongoing and past projects that involve code modernization. So a lot of us are familiar with CCPP, which has provided us with interoperable physics written in Fortran. We've also had Earthworks, which provides GPU enablement through OpenACC directives. We also have StormSpeed, which integrates performance portable Cocos and C++ as a dynamical core. And then we've seen a lot of recent experimentation with JAX. And code modernization generally has different goals. So sometimes we focus on complexity containment. Other times we're interested in physics package portability. And then also GPU enablement is obviously a very popular thing to work on these days. And so primary industry support currently is focused on Python and C++. And we're seeing significantly less support for Fortran, and notably even less for Fortran on GPUs, which is sort of a problem as we move into more and more GPU-focused hardware. And a lot of graduate students and postdocs, myself included, maybe aren't as familiar with Fortran. And a lot of younger career scientists are mostly learning Python. And so this project is largely interested in exploring how multi-language support can impact community contribution. And so again, we've seen StormSpeed with C++ dynamical cores in a Fortran application. And then this project sort of is the opposite of that. We're looking at pulling Fortran physics and plugging them into a C++/Cocos application. And so to do that, we're using the DOE's Energy Exascale Earth System Model, or E3SM. And so this is kind of their Earth System modeling framework. And the goal of this framework is to provide Earth System modeling capable of exascale simulations. And so today we're going to focus on the atmospheric component, which is EMXX, which supports, has native support for language interoperability for parameterizations and physics. And then it also provides hardware portability and performance on GPU since it is written with Cocos. And so really briefly, interacting with E3SM is generally fairly familiar to those of us who work with other atmospheric codes. And so they primarily rely on the XML change functionality to change ComSet, grid resolution, choice of compiler, machine environment, bash job parameters, etc. You could also use it to change your simulation runtime, time stepping, sort of all the stuff that we're familiar with. But then they also have another option, which is the ATM change functionality, which allows us to change atmospheric process settings at configuration time. And so it's sort of similar to the CCPP approach, where instead of using XML files, we're just using this ATM change to change them kind of on the fly before we compile our code. And so what this sort of looks like is I can have an ATM change file. It then sets up a runtime configuration for the atmospheric processes. And so if I want to change my processes to say look like shock and then P3 and then MAN4, and I'm not an atmospheric scientist, so I don't know if that's a reasonable setup to use, but for the example, that's what we're going with. And so now we're going to compile the code to have that run scheme. And then if I want to change something, I don't have to make a new driver or anything like that. I can just change the parameters I'm passing into ATM change, and then it will configure it for me correctly. And so we can also use this ATM change functionality to change logging settings just for the atmospheric processes. We can set and change topography files, initial conditions, and etc., and sort of keep it isolated to the atmospheric model if we want. Emacsx also provides sort of some automation and sanity checking, which is really nice. And so it automatically handles grid management and time stepping for us. It also provides pre and post condition checks for all fields, or you can add your own. And so the screenshot at the bottom of the screen is an example of checking to make sure like our precipitation is above 0 at all times, and we don't have any bands in these fields. And then for some of these other parameters, we're making sure that it's within a reasonable bound. And so that's really nice because someone like me who has no domain knowledge really can kind of come in and sort of figure out like, is my code within bounds that are reasonable before I go talk to someone to tell me if it's actually correct. It also automatically handles file IO for you. So you can just tell it what you want to output and where you want it to output it, and it takes care of that. And then also data field management between processes. And so that's really nice. And so as far as adding a new parameterization, you really predominantly only need 5 components. And so constructors, you can put whatever you want in it, but generally they can be empty. We also have a set grids function that we need to set that defines the fields that we want to use and what grids they should be on. We also have an initialize to create our field checking, for example, and initialize anything that needs to be initialized. We then have a run, which runs our physics package for us, and then there's a finalize that can have stuff in it or it can be empty, depending on what you need. And so we started in the fall working just with a identity transform that I was told to name after myself. So we have the Stengel parameterization that just multiplies pressure and temperature by 2 and then divides by 2 and then returns it back. So it doesn't really do anything exciting. And so we've used this identity transform to sort of explore what this bridge code and language interoperability looks like. And so we have the C++ Cocos default. That's kind of, will be shown in this orangey color. We also have a Python bridge, which is the green. And then we have a Fortran example, which will be in blue. And then we also, I'll touch on this in a little bit, but we also have Fortran that has OpenACC directives added into it. And so sort of at a like very high level, what this looks like in practice for our set grids, right? We get our physics grid, and then we tell the field manager, oh, I have a temperature and a pressure value that I'm going to be updating. You can also use this to set, like I only want to read in this field, but I'm not going to change any values. So only give me read permission. And then similarly, we can also say, oh, I'm only going to output. I'm not expecting an input for this. So we're only writing out values. And then this updated option is for read and write permissions. So that's a nice error prevention method. In this case, we didn't really need to initialize anything. So that one's kind of empty. And then for our run, right, we're just pulling the fields that we care about, the temperature and pressure from our field manager, multiplying by 2, dividing by 2, and then we would update correspondingly. When we add the Python bridge, the grid, set grids function looks pretty much exactly the same. And then inside our initialize and our run functions, we're just using like PyModule to call existing Python functions that I have defined in another Python file. And so for the initialization, we just call this a init function, which in this case doesn't do anything. And then for the run, first we use the Python interface to pull in Python compatible versions of the fields, and then we pass them to our main function defined in our Python file. And so it's very seamless. Right, presumably we can do this with Jack's code as well. The Fortran bridge does get a little bit hairier in the sense that we have to create an intermediate level in C++ to then call our C-bound Fortran calls. But essentially, we're adding our C++ bridge code, which is in this case single F bridge init, for example, for the initialization function, which then calls a Fortran function that is C-bound to initialize anything. We don't have to do that in this case. And then for the run, we're doing the same thing, except now we're passing in our variables in, and then that single F bridge run C function is doing the scaling and the division for us, and then returning it back to us for C++. So a few notes on these interface bridges. C++ and Fortran do have different data layouts. So that does require doing a transpose on the fields before and after going from C++ to Fortran and back. And then we've also been using just a struct to keep track of these fields that we're passing back and forth, since we need a C++ and a Fortran layout for them. We have also found out that it does support using OpenACC Fortran directives. And so we can run the C++ code with Cocos and then not have to transfer data from back to the CPU in order to run to the Fortran. We can just keep everything on the GPU and then call our OpenACC Fortran code, which is really nice. And then we can also use this this bridge framework to bridge directly into existing code from other repositories. For example, like Clever Pumas are on the list to look into, but so far we've been working with the Kessler parameterization from CamSima, which is pretty small microphysics parameterization. It's a little under 800 lines long, including the metadata. And then, right, so this has all been modularized for use with CCPP. And so the CCPP generated code is on the order of 1,000-ish, thousands of lines of code. And so to pull this modularized Kessler into Emacsx, I wrote about 1,200 lines of C++ code, which does include a lot of debugging code and comments currently. And then I added about 180 lines of Fortran for that bridge interface to then call the Fortran Kessler. But I didn't change anything in the Kessler module. I'm just directly referencing into it and pulling it. So that's really nice. I don't have to make any changes to existing Fortran code. And so far, I spent about 2-ish months on the Stangle parameterizations, just figuring out how to work within Emacsx. And I don't really know Fortran very well, so had some learning curves there. And then so far, we've spent about 2 months on the Kessler bridge. And again, I'm not a domain expert, so a lot of those headaches involved me not understanding what different parameters should be and if they needed to be converted, or just like details like that. But currently the code is functional, as in it is running and we get an output, at least on a very, very coarse grid. And so sort of our first next step is obviously we want to verify that it's working correctly. And so we're planning on comparing that to F-Kessler and storm speed. But in order to do that, we do have to figure out how to implement analytical conditions into EMXX so that we have matching initial conditions, because it's not really a good comparison if you're doing a different simulation. Additionally, we're also looking at other CAM physics and other general physics parameterizations to port in through the bridge. And so Club and Pumas are on the list for that. And then so far we've only really looked at Python and Fortran for bridge code, but I think it'd be interesting to also bridge into existing Python JAX code, and also potentially explore Rust or Julia code, since a lot of work has been done in those languages as well. And then we've also been working with some other people here at NCAR to sort of lay out a plan for automating bridge code so that we can sort of speed that that bridging timeline. And then as far as portability and performance, we do need to finish GPU enabling Kessler by adding OpenACC directives. And so that work has been started. And then also comparing memory footprints for the EMXX with Kessler versus like F-Kessler and storm speed. And then we also want to look at the comparisons of, we only run Kessler and EMXX on CPU versus the GPU with the C++ side to then the CPU Fortran. And then if we have everything on the GPU, what does that look like? And is adding OpenACC directives beneficial for us? So that's all I have. If you know how to do the analytical conditions, please let me know. I would love help with that. But otherwise, that's all I have. So thanks.
Are there any questions?
So you mentioned you're thinking of doing a JAX conversion or layer. I wanted to ask this in Aya's talk as well. Like, I believe the JAX, the way JAX works is it doesn't really like mutable functions. Like, it always has to return something new when you manipulate it. Is that going to put any like constraints on what you're able to do with this, or is it not an issue in your case?
That's a good question. We haven't really explored that. Like, the only Python bridge I've written was this identity transform. I think there are some other examples in EMXX where they do like actual physics in Python, and it seems to be okay, but I'm not quite sure. I haven't explored it very much.
Okay.
I mean, certainly the Kessler code as it's written today is doesn't hold that property.
Okay.
So it basically updates the existing moisture fields.
But does it also kind of require the output to be an array rather than kind of updating? Or did I misunderstand you?
So right now it's the same array. It just updates the same array.
Right. Doesn't JAX work the opposite way? Like,
Yes, that's my understanding
Okay.
as well. So
sounds like an interesting challenge.
Anything else? Next one, thank you.
Thank you.
Our next speaker is Pranay Kamara from NVIDIA. Thanks.
Hello everyone. So today in this presentation, I'm going to talk about about a loop restruct implementation in column-based codes, where we can use a single code base to achieve optimal performance on both CPUs and GPUs. So going into the agenda, so I'll first start with what is a column-based implementation, and is it good for the CPU or GPU hardware followed by what is a good optimal layout for the GPU architecture, and then a loop restructuring code which can be used to obtain like optimal performance on both the CPUs and GPUs. So what is the motivation for us to have a single code base? As now we are working on different platforms which contains different hardwares, CPUs and GPUs. We need to make sure we are achieving optimal performance on both the hardwares. And when you compare a CPU to a GPU, the level of parallelism we achieve are way different. Like on GPUs, we have a 2 order of magnitude more parallelism compared to CPUs. And to have the optimal performance on GPUs, we would need to do a few optimizations such that we push the loops inside so that we expose more parallelism for the GPU threads. And to do that, we would need to make the changes in the code, which could have a negative impact on the CPU. And because of that, we would end up having 2 different code versions that would run on CPU and GPU independently. But that would increase the maintainability, version control for the code. So what we are trying to achieve is have one code base that can run optimally on both CPU and GPU. So this presentation is mainly based for column-based implementation, which is widely used in several climate and weather models, where generally the outer loop iterates over horizontal grid points, and then the inner loop iterates over vertical columns. So many applications like the tempo microphysics, the vertical mixing algorithms, they slice the vertical levels and process the data on each vertical level one after the other. So this layout, the column-based implementation, is good for the CPU architectures because as we are working on fewer sized vectors in the vertical columns, the cache efficiency is improved. But on the other hand, this is not well suited for GPU because it limits parallelism, which we can get from the GPU hardware. So the alternative for the column-based implementation is the plane-based implementation, where we have all the loops that iterate over horizontal grid points and vertical grid points together so that we expose more parallelism on the GPUs. But a counter argument for that is it would degrade the performance on CPU because now we are working on higher memory that would have more cache misses. So because of these, we would end up having, as I was saying again, different code versions. So in this talk, we are going to show a loop structure that can dynamically switch between the column-based implementation and plane-based implementation using strided-based approach. And in doing so, we can achieve a single code base that can work, that can produce optimal performance on both CPUs and GPUs. So this is what our end goal is, where you can see the red line and the red line, which is the CPU implementation, is exactly lining with the column-based CPU implementation. And the purple line, which is the hybrid GPU implementation, is aligning with the plane-based GPU implementation. So we are trying to get the best from both the layouts. And here the hybrid implementation is a single code base, which we just switched one parameter or stride, and that allows us to switch between the optimal CPU and GPU performance. So to demonstrate this loop restructure, we have developed a standalone code, a C++ code, which resembles Tempo Microphysics layout, or the loop layout of Tempo Microphysics, and we have ported the code using OpenACC. And all through the code and all through the presentations, when I say n cells, it's nothing but the number of grid points in each dimension. And basically, the number of grid points depends upon the resolution, which is in thousands or even more. And the vertical columns is generally less than 200. That's what we generally use. So in this test case, we use the vertical columns to be 50, which is what we are testing the Tempo Microphysics with. And the codes are executed on H100 GPUs. So moving on to the code, structure for the column-based implementation. So as you can see to the right, we have outer loops that iterate over horizontal grid points, and then we have multiple instances of inner loops which process the column of that particular grid point. And to parallelize this column-based layout, we generally have GANs on the outer loops so that we have more threads working on the horizontal grid points, and then we can assign vectors in the inner loops. So doing so, we'll process one column at a time. But as I was saying, on the CPU side, this has an optimal cache efficiency. But on the GPU side, we are losing GPU parallelism because we are restricted by the GPU resource usage. So here is a plot of the CPU and GPU implementation of the column-based layout. As you can see from the plot, it looks like GPU is performing better than the CPU as expected. But are we effectively utilizing the CPU in this case? Like, are we using all the resources we have on the GPU? That can be understood by looking at the profiles and trying to understand what are the limits of thread usage or VOPs usage on the GPU. So one parameter to say if we are effectively utilizing GPUs is to see, are we using the maximum threads possible per SM on a GPU? Like, for example, on a GPU, we can use on an SM, we can use up to 2048 threads. So are we using all the threads so that the VOPs, like different VOPs can be executed by VOP scheduler, and that hides the latency, which will improve the occupancy. So our goal would be to improve the occupancy, which are mainly limited by factors like register usage per thread and shared memory usage per block. These would limit the total number of threads we use per SM. And this is the NCU profiler output for the standalone code we have implemented. And if you see all the way to the right, we are using a total of 256 registers per thread. And since we have only 65,000 registers, 32-bit registers per each SM, and we are using 256 registers per each thread, we end up only using 256 threads per SM. But the maximum we can use is 2048. So it's like we are using only 1/8 of the total threads in flight, because of which the occupancy goes down significantly to about 12.5. So improving the occupancy here in this case would be by reducing the register usage per each thread. And the way we can do that is using plane-based implementation. And here is the code structure of the plane-based implementation, where basically we are pushing the loops that iterate over horizontal grid points closer to the vertical levels. So this way we can collapse all the 3 loops and have more parallelism. So earlier we just had the total number of grid points, like the parallelism is just on the total number of grid points, but now it's on total number of grid points times vertical levels. So we have more parallelism per each kernel. So, but in the, by modifying the loops in this way, we end up adding additional dimension to the local variables, which would increase the memory footprint. And that would affect the cache on the CPUs, resulting in cache misses and degrade the performance on CPU. But on the GPU end, we offer more, we get more 3D parallelism, and the register usage goes down significantly, and that improves the performance on GPU.
I'm sorry to interrupt. Are there data dependencies in your column solvers?
Yes, in one of them. Yeah.
Okay.
So in the compute on k-dimension subroutine, I had 5 loops, of which one of them I had a data dependency, which I had to serialize it.
Okay.
So here is the comparison of both the column-based and plane-based implementations. So moving on to the plots, here is the CPU implementation comparison between the column-based and plane-based. So as you can see, the column-based implementation has a better performance on the CPU end, and we see a 8% performance penalty on the plane-based implementation after certain NCL values. But if you move on to the GPU implementation, you can see that the plane-based implementation has a better performance compared to column-based. It's close to 2 times for higher number of N cells. So as you can see from both the plots, column-based implementation is optimal for the CPUs and plane-based implementation is optimal for GPUs. But maintaining 2 codes would increase the complexity for code duplication. We'll have version control problems, and whenever we develop a code, we need to make sure we include those developments in both the versions. So instead of that, we can use a hybrid strided implementation where we use a single code base that dynamically switches between both the implementations. And here is the layout for the hybrid strided implementation. So basically, the main difference is we use both the loop structures from the column-based and plane-based implementations, but we on the column-based side, on the outer loops, we step through a parameter called stride. So instead of just stepping through one step, we go through stride. And then the inner loops, which are also the horizontal grid points, will iterate through all the way till the total number of strides. So in this way, when we set the stride value to 1, basically the outer loops will be active, the inner loops, the I in and J in, will just be single iteration. So this would become a column-based implementation. And when we set the stride to N cells, the outer loops are just 1 iteration, and then the inner loops would become that would become a plane-based implementation. So this way, by changing one parameter stride, we can switch between the column-based and plane-based implementations. And here is the plot for the CPU implementation comparing all 3 versions. As you can see, the hybrid implementation overlaps with the column-based implementation, which is the optimal performance. And on the CPU side, we see that the hybrid implementation is close to what the plane-based implementation is. And in this case, if you see for higher number of N cells, hybrid GPU implementation does show like it has better performance than plane-based. But we haven't analyzed why is that improvement. But as you can see, the plane-based GPU implementation and hybrid GPU implementation are close to each other, which is basically 2 times of what a column-based GPU implementation is. And moving further, as I was saying earlier, a plane-based implementation, in the plane-based implementation, we generally add additional dimension to the local variables. So the memory footprint increases. But if you see here, the x-axis is the strides, which I was using. So I was going all the way from 1 to the total number of strides per N cells of 1024. And as you can see, as you are using 16 to 32 stride itself, we are achieving 90% of the performance of what we can achieve with the plane-based implementation. So if memory is a limitation, we can use fewer stride value instead of using the whole 1024 stride value for this particular case. So this way, we can, using hybrid loop structure, we can switch between the CPU, the column-based implementation and the plane-based implementation. And as you can see, the column 2 shows the speed of comparison between the hybrid CPU implementation to the column-based, which is close to 1. We have a penalty of 1%, less than 1% on the hybrid CPU implementation compared to the column-based. And on the GPU side, the hybrid GPU implementation is compared with the column-based GPU implementation, which is 2 times. So using a hybrid implementation, we can achieve optimal performance on both CPU and GPU. And this is done using a single code base, and this would eliminate the maintenance of 2 different code bases. So in the conclusion, I would like to say that using a hybrid loop structure would allow us to use a unified code base and achieve optimal performances on both the CPU and GPU architecture. That's all from my end. Thank you.
About 10 minutes for questions. Yeah, Daniel.
That's an interesting talk. So I have a question about what is the plane-based implementation that we needed to add additional dimension to the arrays, or?
So we basically push so if you look at the column-based implementations, we have the I and J loops. So in the plane-based, we are just pushing those loops inside closer to the vertical columns. So this way we are basically each section is its own kernel in the plain base. So we have limited register usage there.
If you have like, I think many physics codes have, they call subroutines, elemental subroutines. Do you just do those like ACC routine vector?
So using ACC routine, what happens is the compiler needs to store the metadata for that particular routine, and that affects the register usage. Like it increases the register usage. So in the plain-based implementation, we try to eliminate the ACC routine usage, so that to do that we push the loops inside the routine as well wherever possible. But again, on the column plain-based implementation, as we are pushing the loops inside, we will have more kernels. So we will have the overhead of the kernels. But if we can overcome that overhead with the performance improvements, then that should be fine.
So you're getting the performance improvement because your kernel doesn't encompass so much state, so it doesn't use as many registers to it doesn't do 4 or 5 different loops. And a function call and another function call and stuff. So you have less register usage for that, which means you use the GPU better because you can have more threads running, which hides the latency. But you also get the parallelism and break it up into smaller kernels. So the smaller kernels let you use less registers.
Yeah, this is great. I love it. This is what the MIT GCM model does essentially. You're basically just dividing the domain into blocks so that you reduce the register pressure, and then boom, you get it. So yeah, MIT GCM model does this, and we've talked about doing the same thing in the MallMotion model, because we've only looked at this really from the CPU end, but we've recognized the performance bottleneck, and we wanted to kind of figure out how to get closer to the peak. The question I have is not for you, but really for your NVIDIA overlords. This feels like something that the compiler might have some wisdom to work out. Like if it can kind of correctly infer that there's sufficient no data dependencies. Is there a way to get to the point where the code can kind of do this blocking for us? Because when I look at it, there's this stride parameter, but it is ultimately going to be a machine dependent parameter. And I would prefer not to have to tune it. I prefer to have to just hand it over to a compiler that knows my target and then just set it for me.
I think this gets back to the code reproducibility of Bitwise, right? Because Bitwise different. How you wrote your loop. You said, I want to do this loop this way. Put a stride in there. It's a different loop ordering now.
Not necessarily. I mean, for the kind of solvers we do, where we kind of have left-hand side is applied to right-hand side, order of operations is not an issue. Like for us, we would be happy with something that did it for us, and we would get the same answers. Or we believe we would.
I mean, I think you could have like an AI tool that rewrote. This is just basically like
that's true.
This is like cache blocking, right?
Yes.
Cache blocking, but except we're not really doing it for the cache as much here. There's an argument for that. We're doing it more like you could call this parallel blocking or something. You're doing it because I want the more parallelism, and it actually you could pick stride to be perfect here, like Pranay showed. Like, well, a medium stride is pretty good too. You could pick perfect strides even in the other dimensions, so that you get what your goal really would be for a perfect code would be as much parallelism as I need, but no more. So that way, hopefully, I'm very fresh in L2 and L1 cache. Like I need this much parallelism, so I got to go this big of a domain. But doing a way bigger domain is overkill if you are exiting your L2 cache between kernels. But I'm not sure that the compiler couldn't do this. I feel like the compiler would say these are not necessarily the same codes and they're not valid.
Well,
a human can see it. And that's where maybe an LLM model could say these are the same thing, but a compiler is so rigid of like, nope, I can't prove this.
Well, I have examples where I know the compiler will safely swap my J and K, four blocks. Like that's a pretty aggressive move there, but it's able to kind of ensure that it's safe.
Huh.
I mean, if it can look at sorry, did someone else want to?
Sorry, go ahead. Please go ahead.
Oh,
no, please go ahead.
I was just repeating myself. I believe there are times when a compiler, or at least could the programmer, maybe do something to signal, like something like the restrict keyword, say this is safe.
Like in some examples, like I haven't seen this, but talking to compiler people, what they mentioned was for smaller code sets, like for inlining, if it's a smaller call, a function, the compiler would automatically incline. But if it's a bigger function, the compiler would not inline that because we don't know what complexities would that bring.
So that's the other problem here is like, Pranay showed it as like, there's not a huge call stack between, the outer loops and the inner loops, but in a lot of other codes, like FP3, we looked at one time, there's a huge call stack difference. And that's where like this effort of pushing the parallelism down close to the other loops is like kind of hard. Because you actually like have to like, well, so I pass it, like, it's 5 call stacks away, and you don't get good results if you put like ACC gangs out here, and then way inner here you have like a bunch different things where you're putting the vector in, because it's this huge thing you're trying to put into a kernel and all these call stacks that eats up registers of like calls. But so that's why you want to push it down. But if you do the stride manually, and the compiler's gonna have trouble seeing through all those calls. That's really, I mean, maybe it could do the for loop thing, but it's not gonna see through 4 call stacks correctly, improve, yeah.
Yeah, although compilers are okay with going a little bit and then giving up. They have a tradition of that. So I don't know. I'm dreaming up something because I don't write compilers. But it feels to me like if I can naively split this loop up and do some annoying integer arithmetic to figure it out, I feel like the compiler could do it better than me, and even more importantly, know what the target is.
Yeah.
Okay, so we have a break until 3:00. I think there's going to be ice cream out in the outer Damon room, and there will be folks from CGD and Sizzle that are not in the meeting coming to socialize with us and eat said ice cream. Our first talk after the break is Marshall, so maybe we could get your machine set up a couple minutes before it ends.
Do that early.
Yeah. Okay, great. Thanks, everyone.
I don't have to use my computer.
Oh, good. Okay.
I could just.
Yeah, I know. I'm hoping.
Yeah, so that is what we are
So there should be some left.
Yes.
Thank you for coming. Yeah.
Oh, we
No, I live on the way to Longmont.
Okay.
It's unincorporated Longmont, near the IBM.
I'm sure it was.
Yeah, my neighborhood was built for a housing.
So I was talking to David about the data project. So David was leading the.
It looks great.
Yeah.
I don't know why. All right. So I think
So what is the estimate for us to pass coded?
Which actually at that point.
Have the.
Oh. Yeah, right. No, it should see, yeah.
Yeah, but. How much is the job?
Yes.
Actually want the job, they're not changing it. And that's like, you know. Yeah, but that would be a big difference. File this code that's. All these options. Right, that's what you.
You got to first translate. We don't have time.
So you're Fortran, right? Yeah. I've a way to template in Fortran.
What?
I've a way to template in Fortran. I think I sent you an example of how to template in Fortran. That's the email I sent you.
Steve's not officially doing
elevator pitch.
Yeah, yeah.
Yeah, I know, wait, yeah.
It's just like I
I think it's your slides.
It's unhealthy.
Is this yours? Or someone else? Okay, well, you're good.
Okay, so we have 2 more talks and then a little bit of time for discussion. So Marshall Ward is here from GFDL and he's gonna talk about porting Mom 6 to GPUs.
Hi, thanks everybody. It's the first time I've actually made a proper presentation of this stuff, although some of it will be familiar to a few of you. We've been trying to get the Mom 6 code base on the GPUs for a while, and I think we finally have some results that we're able to share that we're pretty happy about. It's been a team effort. My name's first here, but to be honest, as time goes on, these other 3 guys have done all the real work, and I've really just been juggling the PRs. It's Ed Yang and Jorge Galvez Vallejo in Australia, and with Thierry Wagura, who's in the lab with me at GFDL. So I won't go on too much about Mom, but I wasn't quite sure about the audience, so I put a little slide here showing just to kind of gently introduce into it. Pretty little movie, maybe you've seen it. I think it's CM2. Mom 6 is an important. Mom 6 it's a model used in NOAA. It's used in NCAR. It's used in many places around the world. It matters a lot. It's in research. It's in operations. It has its own way of doing ocean modeling that a lot of people appreciate. But most importantly, for this purpose, this meeting, it doesn't run on GPUs. So we have a challenge, which is that this is a community code that it affects a lot of people. So we touch one part, we're going to hurt a lot of people out there. And it's used in all sorts of operational work, forecasting our environmental prediction systems in NOAA. It is a Fortran code base. I'm not going to say legacy Fortran, as I've heard a lot of people say in this workshop. It's a modern Fortran code base. It's a fairly large one. I won't say it's huge anymore. I've seen bigger now. But 200K is a lot of work. Maybe not for an LLM, but it's a lot of work for a person to port. And there's a lot of things that can break. I'll just say for the purposes that changing answers hurts people. And so if we were to change them, it would be a disruption that we would have to take on board. It consists of a lot of solvers, some working on layers, some working on columns, some doing things a little bit different. There's no really one simple answer to porting the model over. And even within each solver, we have a big community. Lots of people have different ideas on how to solve these things, and each of those, it's reflected in the solvers themselves, which essentially means lots of if blocks and things like that, and free parameters. So the question is, can we balance those needs in a way that doesn't disrupt the work of all that's going on? Again, this is another slide. It's a little too trivial for this audience, but just to say what's going on. If we want to program to the GPU, what we really have to do is take those solvers, chunk them up into units of kernels that can be sent over to the GPU, and then have a driver that steers the whole thing. And of course, you can divide that labor as you want. But the thing is that I have to remind myself is there's more than one way to write a kernel. There are lots of different kernels out there. Python can generate kernels with Numba. You can write kernels in OpenMP, OpenACC. Julia has its own way of doing things. But the one block here, is my mouse show up in here?
Yep.
It does, great. The one thing here that I'm calling out is the do concurrent construct. And all these things do eventually translate in their own way to the GPU bytecode. But the one I want to really talk about is this do concurrent. And first of all, is it a kernel and is it viable for us? And just if people aren't familiar, do concurrent is a not terribly new, I mean 20 years new, but it is a new feature in Fortran. It's does not say it is, I think the way to phrase it is it's to promote parallelization. It is not itself a parallel construct. What it says is that the contents of the loop can be done in arbitrary order. It's sort of a computer sciencey definition of concurrency. But once you have that, it is sort of a necessary condition to get parallelism. And so there are conditions here. I'm not going to read them out just to say that the iterations can't depend on each other, and you can't mess around with the operating system and anything out there that might have state. But it's a little bit more than that. It's a little ideal to expect the compiler to catch everything. To use this thing, you really have to be a good person. You have to, it's a little bit of a contract, like compared to the C restrict keyword. You know, you can put that word in there and you get kind of a level of safety that is your responsibility. And maybe someday compilers can check it all, but but when we write do concurrent, what does NVIDIA interpret that? So I should say this is going to be an NVIDIA talk, but I think that is pretty much the most practical path to GPUs. So when NVIDIA looks at this do concurrent loop, it says, okay, I'm going to treat that as an OpenACC kernel. And the only real difference here is it doesn't literally do this. It kind of interprets it as the same and it dumps it into the bytecode. But I would say the one unique thing is that it does assign what we call a vector length, which is the number of threads per block, which is a chunk of work sent to one of the chips on the GPU. But the point being that there is kind of some hard-coded decomposition of work done. And this is sometimes tunable, but let's just say, all I really want to say is that the compiler is sort of putting a little bit of opinion, let's say, on how this thing ought to run. One interesting thing about using do concurrent is that we can do what are nested do concurrents. So this is kind of a way of establishing that there are higher level and lower level concurrency going on. So I don't quite know what it means or if it's supposed to mean anything in terms of the Fortran language standard, but what we can see is that it does trigger a more elegant decomposition between, again, what we would call teams in OpenMP. In OpenMP language, we would call them teams, which are the units of work sent to the chips, and the threads, which are the work itself going on inside the chip. So every language has its own terminology. The interesting thing about this is that because it's OpenACC, it exposes an additional layer of abstraction called the worker, and that allows it to do somewhat more interesting grid and blocking decompositions. I think I'm not going to get into what these numbers mean. I do explain it on the slide, but I think the point is that you can establish more sophisticated grid decompositions of the work as it's sent to the core. The one thing that isn't addressed by these do concurrents is how you move the memory around. So there are automated ways of doing this in the compiler. There's shared memory, unified memory, these things. But in our experience, the compiler is just not doing that great a job for us in our code. It may be a reflection of the size of our code base. It may be a reflection of the complexity. But what it comes down to is that we opted not to use it. It was very, very slow. So instead, what we do is we do manual memory management, which is a bit tedious, but it is just, we manually sort of create the fields on the GPU. We manually transfer data into them where necessary, and then we execute the kernel with standard Fortran. But at this point, we sort of assume that everything's already been laid out for us. If we get those assumptions wrong, this will trigger unnecessary data transfers. But if we get the assumptions right, it's a very fast operation where no data has to move between GPU and host. So the syntax here is we are allocating C. Oh, this is wrong. This should have been allocate A, and this should have been 2BC. I apologize. But we allocate the result. We copy over the inputs. We run the kernel here. We save the results of B plus C into A, and then we save the host. You can see I got the labels wrong. I apologize for that. But we would save A onto the CPU and delete the B and C. Please, my apologies for those getting that wrong. You know, taking all that in, we do have a strategy that we try to adopt. So data transfers are expensive. So we have had the ambition of doing everything on the GPU. We don't want to move anything back unless we have to. And hopefully, at least up to now in the problems we've been working at, we haven't had to. It does use a lot of memory, but so far it's been pretty tolerable. So as I mentioned here, we don't do manual memory management. And the third part here is that we're going to use do concurrent where possible. It's not going to be everywhere, and I will explain at the end where problems can occur. But in general, we're going to try to do as much computation on the GPU with kernels defined by do concurrent. So I do have results to show, and from those results, we're using what's known as the double gyre configuration. It's an old classic problem. It demonstrates the Western intensification problem where gyres form on the West. It's called double gyre because the domain allows two of them here. But we're just going to run what are initially simple grids of 32 by 32 points, and then we're going to have 100 layers. This is the 100 layers to at least try to kind of capture the workload that you would see in a more serious production run. So the way I put it, the calculations are not serious, but the load that we're working on is. And so to stress test what we've done, we're going to take the 32 by 32 and continuously grow the domain up greater and greater to do a weak scaling test. And for dynamic reasons, we keep the spatial grids the same. So we're physically increasing the domain size here. And I'm not showing you how we converted the kernels individually because that's a very long and a different talk. But take for granted that we have converted as many kernels as we need to get the double gyre experiment to run on the GPU. So what I'm going to compare is what are the Genoa Zen 4 CPUs, 96 cores, and I'm going to compare that to an H100 NVIDIA GPU. So this is not a shining result, but it is an interesting result. So when we run this, we are able to get equivalent timing so far on the CPU and GPU. This is with fairly minimal code differences in our current form. But the way I interpret this is that we didn't screw up. So we're at least getting the numbers on there. And so what I say is that stages us to start thinking about performance. So on the x-axis here is the number of 32 by 32 domains that you see. So this is a log plot. So on the bottom, it's 32 by 32, then 32 by 64, and then all the way up to the end, which is 1,000 by 1,000 grid. It turned out to be a coincidence a little bit. So this dashed line represents when we run out of CPU cores. So to the left of this dashed line, we are assigning one CPU core per 32 by 32 domain. There's a reason for that. That's always been a bit of a sweet spot for us in terms of performance. We've always seemed to get best scaling in the 20 to 40 domain size. So what we do is we scale up CPU here, and then we run out of CPUs, and we just keep going. And that's so we can keep comparing this to the GPU. The GPU, we don't necessarily have as much control over the amount of resources that it's pulling in. But that's the idea here. It's meant to sort of represent device to device. And we compare a single socket to a single card. Again, it's a difficult comparison to know what we're comparing to. Probably it means the numbers are not necessarily literal. But the idea is that on our nodes, at least, they're double socket and they have two H100s each. So for us, this is kind of a typical reference comparison. The answers we get are a bit reproducible. This surprises some people that I talk to. Others don't seem to care very much. But but it is when I say that we don't want to disrupt operations, this is a very good result. We can run things on the AMD chips and get the exact same answers to the bit to what we get on the H100s. This is not just useful for the reasons I said before. This is probably the only reason we've been able to do sustained development. It lets us basically make a change, port a kernel, run it for 20 time steps, make sure the answers don't change. And every time they've differed, it's never been for a physical reason, it's because we screwed up something. So it was vital for development, but I think it's vital in order to get the community to embrace this work as well. So before I showed that kind of bland curve, which depending on your perspective is very exciting or very bland. But if you break it down, there is a reason for that difference, and it varies across different modules. So for example, if we look at the two modules on the left, this is the Coriolis term. Well, it's the Coriolis and advection. And on the bottom, it's the horizontal viscosity. We see that the orange curves, which are the GPU, are much slower than the CPU for these smaller domains. As we sort of get to that 1,000 by 1,000, they do sort of converge to a point, although it really is because the CPUs run out of resources. These are very different solvers. These are K layers. So these are where we're operating level by level, and we're doing each level as an independent kernel. So it's a very inefficient model. But it as a first attempt, it worked. As we go to the right and look at the other solvers, though, the GPU is generally speaking outperforming the CPU. The continuity and vertical viscosity are about twice as fast. It's not easy to see on the log plots, but if you can see the little dashed lines, you can make it out. And the pressure solver and the barotropic are many times faster. So in a way, we don't necessarily need to look at the performance as just being one for one, but more that these components are acting more as a bottleneck to much stronger performance. On top of that, I just showed one socket to one GPU, but we can do NPI communication. We can scale this thing up pretty much as high as we want to. If we're doing Halo updates, for example, we move the Halo content into a buffer, and then that buffer is sent by MPI to the other node. It could be another, in this case, another GPU. If it's on node, if we had NVLink, it would use NVLink, which is very fast. We don't have NVLink, so everything we do, it copies it back to RAM on the CPU, does a regular MPI data transfer, and goes back. So in fact, it's using the very pattern we've been trying to avoid, which is copying data back to the node. But it works. In fact, if we look at the scaling from 1 GPU to 8, we do see a kind of efficiency here. When the problem's small, we're losing time to communication. But when we go over to the larger domains, we generally see a scalability and an increase of runtime as the GPUs are increased. It's not ideal. We're not getting double having runtime with doubling GPU. But it is working. And again, if you do the breakdown, you can see, I don't think this needs to be looked at much deeply, just to say that you do see scalability in each of the individual modules. This figure I flipped on you. This used to be horizontal viscosity. Now it's the message passing time. These times are in milliseconds, by the way. This is per time step. The communication is not what I would want to see, but generally, it is fairly flat, which means it's doing what we would want. And if we can kind of figure out ways to improve the communication overall, we might see a general flattening of this entire time. For example, maybe finding a machine with NVLink, like you guys have, would drop that immediately. The other thing I'll call out is that on the continuity and vertical viscosity, we are seeing true scalability. We're seeing a halving of the runtime as the GPUs are increased. And if you're asking why I didn't go any higher, it's because I'm not allowed. On Ursa, the machine I ran these on, I can only run on Windfall, and they won't let us run more than 8 GPUs. Does this work? I think it works in a lot of ways. The code is dead simple, so scientists should be able to write it. That didn't come out the way I meant it to. But it doesn't involve complex data structures or anything like that. You can just write do concurrent, and as long as somebody somewhere gets the data transferred right, it should be, nothing should really need to change. On top of that, as an argument I made in a chat earlier, it pulls on standard Fortran. If this thing is not behaving the way we want it to, well, then we can call up our vendor and say, please fix it. Again, it's a single code base for both. So the CPU and GPU, we can keep going on operation research can continue on the code base, and we could just keep going. And I'll just say this, when we do get these do concurrent OpenACC blocking, we can get the sort of smart block geometry, but maybe I didn't really call that point out strong enough. How am I on time?
Yeah, like a minute.
Oh, all right. Like a minute in questions or a minute?
I think a minute.
Oh, all right. Okay. I'll very quickly step through some of the problems that we have because it's not all perfect. So one thing is do concurrent, at least on NVIDIA, currently does not support local array declaration. This is a tri-diag solver we have. In the K-axis, we can't do it because it won't let us declare a local array. So when that happens, we fall back to OpenMP. Derived types are a big mess. So this is our grid derived type. It has various fields like the grid spacings. Those have to be handled separately. So if you do data transfers in G, you have to do similar ones in the individual arrays. And I don't have time to explain exactly why here, but if you get it wrong, you can clobber the old addresses and lose everything. It's a problem. We can't do objects. This is not a Fortran issue. This is just GPUs have not thought about supporting, handling things like vtables on the device. You have to kind of find other ways to avoid referencing any kind of complex object like derived type. And finally, we have an issue with function inlining. If our function calls contain derived types, they won't inline. And if they don't inline, the performance falls off a cliff. And in fact, just to kind of end, one of those functions I showed with terrible performance, this was the original performance, this orange line, and the blue is the CPU. Well, if we just sort of hack at that function and eliminate all the derived types and just pass the raw data, the performance actually pops back down, and we get much more competitive CPU timing. So that might ultimately just be a compiler bug that could be sorted out. And I'm out of time. I don't know what to say. All right. Ask me about async. We're very excited about this, but there's a way we might be able to eliminate some performance issues with kernels. Let's forget that and let's go there. So yeah, I'll just sum up. I think this is the first time we've been able to kind of run anything of meaning on the GPU with the Fortran code, and I think we're pretty happy with the progress. We have a long way to go, but I think we've met a pretty good milestone on the work.
Does anybody want to ask about async?
Do you have any standard parallel? Can you nest do concurrent and then function call, and then you want to do concurrent inside that function call? Did you run into that?
Yes, we do have that. What we have, do concurrent. Yes, we do have examples of that.
Because I can easily see, okay, do concurrent, tightly nested, okay, just becomes collapse or whatever.
In fact,
can it work the other way?
The example I whooshed through of the function where we eliminated the derived types has an example of that.
Okay.
So yeah, that is very much a possibility. That's how we plan to handle the equation of state. So the objects, which I said don't run on the GPU, actually, that's a bad example because that will be on the CPU. But yeah,
okay,
there are examples of that.
Okay.
Yeah.
Cool. So, I mean, maybe just clarifying. So, how much of the total MOB6 code is it all kind of now running on a GPU, or there's still stuff that's all CPU? And okay, yeah,
Just the RK2 time step and just the parts that are needed to get double gyro running.
okay.
I mean, just our timeline has been reach that point, which we did. Spend a few months thinking about performance, which we have.
Yep.
Now I think we're going to go back to try to get a more complex code on, which won't be a production code still, but it will have a lot more. It'll have a lot more that we need.
Okay, but at least for that double gyro example, all of that computational code is GPU. Like the example you showed for performance, it's pretty much all.
That's
okay.
right. That's
Okay.
right.
Cool. Yeah. Thanks.
Thanks.
Hey, so our last talk before the discussion session is John Dennis from Sizzle. And we'll be talking about GPU Mom6 stuff in a slightly different way.
All right, so yeah, so this is the same end goal desire, but with a quite different approach. And
We're friends.
Yeah.
yes,
We're on the same team.
Yeah.
so this is the Turbo project. Well, I'm assuming that not everybody knows about this. So it's enabling Mom to efficiently use both CPU and GPU based systems, and enable cutting edge oceanography. And we want to gain access to all leadership class systems at NSF and DOE because we've been locked out of DOE systems because we simply can't run on them. And so this was a 5-year cyber infrastructure sustained innovation thing grant. This was actually we wrote this up and they reviewed it, and then GFDL started on the GP enablement work. So anyway, but this is a collaboration between CGD, Sizzle, Texas A&M, and GFDL, and we're at the beginning of the project. So this is a Turbo team headed by Gokhan. CGD is handling the oceanography and community software support and development. Sizzle is for the GPU enablement and optimization, and Texas A&M for the educational training. And so one of the motivations, I'd like to point this out, is this NSF Horizon system. This is a $250 million investment. It's located at the Texas Advanced Computing Center, and it's being installed now. And about 20% of the capability of this is CPU, and 80% of the system capability is GPU. And so this is not a future system. This is like a summer system that they're going to be opening up to new users. And so we can't just not use 80% of a massive investment. So we need to get there, and we have 2 approaches to get there. Some of the motivating use cases, I won't go into this too much, but the last 2, which are 1/36 of a degree, either forced ocean sea ice or fully coupled. These really need leadership class computing systems. All right, so Turbo software approach, this is where we differ slightly. So we want to evolve the code base that can effectively utilize both systems. That's a common goal. So it's going to have two kind of components. We want to create an alternative for the flexible modeling system, FMS, that is GPU enabled, and evaluate the viability of a pivot away from Fortran toward an alternate language approach for the Earth system modeling. And this is probably the biggest difference here. And we're going to ultimately decide upon the path forward at the end of the year 2 of the project. Some of the, you say, why pivot away from Fortran? It's really limited lower quality vendor support for C++ and Python. It's buggy support for Fortran and GPU. We've had multiple big projects that have been hamstringed by poor vendor compiler support. And so what this does is it basically delayed access to new hardware. When they put these huge platforms on they turn them on, we don't want to wait 3 years to get our codes working on them. We want to be able to jump on them when they give us an account. So Fortran also has limited software tooling, and there's also workforce challenges associated with Fortran. You saw this in the earlier talk by Ren, is that the future science leaders are learning Python. Not Fortran, what? Amryx, you may see a common theme here. The kickoff talk was Amryx. And then the next talk was, or I think it was Amrex. So you know about this. Supports both CPU and GPU. It's an exascale computing project used by a number of different domains, assumes logically rectangular grids. So it has a long history of Fortran compatibility. So it kind of grew out of a desire to move a Fortran code to modernizing it. You've probably also heard of Cocos, and so Amrex provides more infrastructure versus Cocos. So you get some of this stuff for free. So this is what we're kind of the software that we're creating. And I color coded it blue for Fortran and kind of yellow for C++. You see the MOM and the FMS interface and the FMS. This is all in blue and Fortran. What we're creating is the dashed lines, TIM, which is the turbo infrastructure for MOM, a nice little nested acronym, and ProtoMOM, which is a prototype, what MOM might look like if it was written in C++. And then there's a TIM interface so that MOM6 could use TIM, and then TIM is based upon Amrex. So kind of the layer cake. So some of the relevant software, Amrex, we've already heard about that. FMS, a NOAA product, FMS interface. So this is basically MOM calls into this FMS, to this interface. And then so we're going to be creating we're in the process of creating a TIM interface, which looks just like it. And so that allows you to link against either FMS or TIM at compile time. TIM, which is the alternative to FMS, and then ProtoMOM, which is a C++ based prototype, and it's under development. And it implements the double gyre test case that Marshall has working. So the timeline of the project, we're somewhere here. We'd like to have a prototype available for people to look at in the summer timeframe. This is pretty aggressive, but I'm still optimistic. And then kind of make a decision whether we move forward with Fortran code base and directives or C++ plus a kind of a C++ and Fortran. And you know, I did some color here, so it's blue and it's going toward yellow, which is the C++. So current status, we have MOM6 build integrated with Siemens. This was quite challenging. We have multiple continuous integration running, MOM6, FMS, TIM interface, ProtoMOM, and C++ prototype classes. So this is kind of the test-driven development aspects of it. We have PF units for the FMS TIM interface. We have about 30 of them. This is you can come and paint fences, increase that number. We have GTest for ProtoMOM, 52 of these, and C++ prototype classes, and we have 15 of those. It's always nice. I mean, I go back, I copy my slides into the new presentation, and I realize, oh, we've advanced unit tests by some number. We're able to execute MOM6 using the first non-trivial Amrex code. So today you can basically link against TIM, and you can use 4 or 5 functions out of Amrex. And it's just normal MOM and it works. We have a reduced complexity version of FMS2 and the start of the ProtoMOM. This is kind of the MOM software dependency tree that's very clear. And this is the modules. And so the yellow there is what the FMS is what we're kind of looking for the alternative to. So something more about the ProtoMOM. And again, this is coming up with a name, had to have a name. So this provide an example of a future C++ based MOM might look like. We want to have the same model configuration interfaces. So, when oceanographers drive the car, I don't want to move the steering wheel around. because that's annoying and then they won't like it. Ability to correctly simulate the double gyro test case, utilize a C++ driver. We want to provide examples of science code that is written both in C++ and Fortran. Must be readable and modifiable by a Fortran programmer. I've looked at this code. I am a Fortran programmer and it looks quite readable. We are willing to give up some of the advantages of C++ if that means it stops looking like Fortran. But hopefully, I don't think we need to give it up. And of course, it executes on both CPU and GPU. This is kind of a sketch of what it looks like. So basically, this is we're taking the solo driver that's currently written in Fortran and we're rewriting it in C++. And so the green indicates sections that have already been rewritten in C++. The red is stuff we're going to defer for now. And then the blue is existing code. And we would love to be, so basically there's this blue line. So it'll be C++, and then there'll be a bridge into Fortran. And then you call all the Fortran code base. And that Fortran code base can be the GFDL work that's GPU enabled. And then you bridge back into Fortran, back into C++. And so that's the goal, is to kind of have this dual language version of the code. And so this allows gradual conversion from C to Fortran. And so that's the goal. And questions?
I had a question about your sort of timeline slide, because when you first started, I thought, oh, I guess you've made your decision, but then it looks like you're saying that July you're going to choose. So have you already decided it's AMRX, or are you still thinking it might still be Fortran only, or?
It might be Fortran only. I think it's, I think that's a big decision, and that's GoCon's.
But you haven't decided yet, or
Right.
the project hasn't decided yet.
That's correct.
Okay.
And and we need to have more. So we need to show what a C++ mom might look like to the community. We need to have some more experience with it and feel what the sharp edges are to this. And so we don't have enough experience yet.
I mean, from our side, we still think there's going to be limits on what we can do on the do concurrent side. And we need to figure those out before that decision can be made, because it could be quite severe.
Yeah. And, it's language, Fortran is very challenging. I mean, I've been involved in many projects, and, you try the directive and you're elated because you get great results early on. And then you start to grind down, and you suffer from huge delays because the Fortran compiler's busted and you grind to a halt.
I just want to ask you if in the decision point you do the Fortran, I mean, obviously assume we still want to get it on GPU. So is then the goal be to use AMRX to still do the GPU offloading, or to go to this do concurrent, or do we not know yet what the?
So the theory would be it would be fundamentally AMRX with pieces of Fortran, and the pieces of Fortran could remain for potentially a long time, and it could have directives in the Fortran for an extended period of time, because you don't wave a magic wand and do the 200,000 lines of code.
Right.
And unless, of course, AI is going to design.
Yeah.
I'm working on the wand. So.
Which I'm perfectly happy with accepting that wand if it gives it.
Maybe that's why I was confused, because it's sort of, you have decided that you want to do AMRX, I think.
Correct. So basically we want to use AMRX to provide an alternative to FMS. We haven't decided whether we're going to do the full model in AMRX.
Okay.
Yeah.
Are there more questions for John? Stop sharing your way from this to group discussion. Most of the chat. So I guess before we really dive into the discussion, the two points of business I want to bring up is one that we had a ton of admin support. So we have Elizabeth and Daniel online. We have Teresa and Caitlin outside, and like they did so much of the heavy lifting to even make this possible. So we should say thank you. Secondly, the part that I'm most excited about is happy hour down at the Southern Sun. So I feel like we should get a show of hands of how many people, like how big of a table do we need? How many people are interested in stopping by? Maybe. Okay, so like maybe one of the big.
It mostly depends on who has the kids tonight. Yeah,
It
looks like there was a question, by the way.
Oh, I don't think I know how to scroll through the chat.
It's right there at the bottom
just
one.
be that one.
Chuck?
Okay, how do
Yeah.
you make a power choose 51?
I guess it's for me, right?
Yeah.
Are there routines that can pre-calculate the optimum vector lengths for various code modules? I mean, there's not routines except that you can tune your code, but basically it's often 128 was found good with OpenACC a long time ago. They've stuck with that for a long time. It's not necessarily the best choice for everything. 256 is often a good choice. And with OpenACC, you can choose that. You could tune that. It's easy, and you would want to maybe tune that. With do concurrent, it's like hidden under the hood that you can't tune that. At least as far as I understand for do concurrent, I don't think you can change it. But for OpenACC, you can change it, and you should change it sometimes. It's good to try different things. We write kernels different ways. Sometimes it's much better to choose a different size. Especially if you know that one of your loops that you're applying the vector to is only going to be usually 32 long. You wouldn't want to tell it it's going to be 120. Like I better use 128 threads to do something that's every time only 32. So that's when you would really kind of want to change it. So
We have played with that, by the way. We've sometimes replaced our do. We had someone replace the do concurrence with OpenACC and try a larger number. And we would see a speed up. Sometimes it would be about 30–40% faster. And you could even make that number a function of the variables, have it max out at 1024 or something.
yeah, you can often write like,
Give me runtime determined.
right, I should make my vector length like 128 or the minimum of 128 or your loop bound or something, so it fixes itself. So that's kind of along the same lines that you were saying. We'll have to see how the do concurrent works. For Mom6 if you stay with directives though, you could still if do concurrent, some sections aren't working well enough. OpenACC has a history of being pretty fat. You can do a lot more flexible things than what do concurrent will stick you with. But it's nice to just mix the whole thing, right? Like you could mostly do a do concurrent and do a couple specialized kernels differently.
That's kind of what we're going for at the moment.
Anybody else have things they want to bring up? Maybe probably should have thought of some questions ahead of time.
I have more comments or
Yeah,
what? I
go for
have
it.
comments on the Mom6 stuff. One thing to keep in mind for GPUs is that, when you showed your plots, what's happening is that the GPU is not that saturated really at the beginning. At the 1x case, it's not even 1x case was not enough parallelism to saturate a single H100.
It also doesn't even represent anything close to a production run for us.
Yeah. So as you can comment, that's sort of what's happening, right? It's sort of the same as your CPU where you're we're only using one core of the CPU, right? So you get flat performance for a while because you're really not saturating your full socket. You're just doing one core and you're adding another core. So then eventually you saturate your CPU, socket, and then you also saturate the GPU, even though you don't think you're adding more, you're not adding any more GPUs, but you're not really saturating it until a point where you are. And then they both should go up, but they might go up they might saturate at different points. But in general, you need to saturate the GPU, you're going to need 32 by 32. You're going to need about 200 of those, not 100.
Yeah, we know we're saturating it, but we're saturating it badly, I think.
Or in the other case,
Is
where
what
you
it-
showed your slow, some of the slow things where you went level by level, all of a sudden you're doing a lot less parallelism, right? You're only doing 32 by 32 parallelism. So that's definitely way undersaturating, which is why, you know, GPUs are throughput devices. If you gave it more, it would do it just as fast, but you're not giving it as much.
I mean, for those loops, which I didn't get to show with the async, we know that a lot of the time we're losing in those functions with the very poor performances, kernel start stop. Because I mean, we clocked it. The time to start a new kernel is just as long as the kernel itself in those functions. So we know we're very heavily kneecapped in that case.
So John mentioned like some issues just with the compiler and the Fortran support. Are either of you like even remotely involved with the compiler team, or is that completely separate? Like,
pretty involved, yeah.
So we can email you.
I mean, is there a plan to improve the Fortran support, or is this really just like the roadmap? Is that
No, so Fortran compiler support is improving. We are basically going to an NV, we're calling it, I don't know what we're calling it, so don't quote me. We're going to a Flang base, and sometimes we're calling it NV Flang or something, but we're going to Flang. We are contributing. We also want other people, anyone to accept OpenACC. We think OpenACC is a nice thing to do, and it shouldn't necessarily be only NVIDIA. We're happy if, like, say, AMD would take and make OpenACC work on their chips well. Like, they kind of have it on certain one-offs for like Frontier had it for only Fortran and stuff. But my whole point was we're giving the infrastructure into open source Flang for OpenACC. Like, it's all built in the front end part. The back end of how to do it is not there, but the parsing and all that up there, we're putting that in. And we have codes now where we have like a lot of object-oriented Fortran, a lot of inheritance and stuff that won't compile with NV Fortran, the old, current Fortran. And we're trying out the new Flang-based Fortran compiler on it that we have in-house, and they're working. They passed all the tests. So it's showing that there's progress. I mean, John's talked to us a lot before, I think. And my take would be, I think we've been working on fixing it. We've maybe fixed it. And probably for John, it's like, too little, too late, or something. Like, he's kind of, hey, we're almost there, but you're moving on, and that's okay.
Well, I mean, what it will be is we submit a bug report, and then you fix it, and then something else breaks, and so you get to the point where no version of the compiler will actually work, because one will break restarts and the other one will break something else, and so you're stuck.
Yeah.
Right. Do you want to leak memory at 30 megabytes a time step, or do you want to not have restarts?
Right. Yeah. And we
and the answer is both of those are awful.
Yeah.
And so when they don't get fixed for an extended period of time, it's like, kind of, what do you do?
Right. But I think we also discussed how do we get. I think we had CESM1, in the compiler regression suite, and then we just had it in there forever. And we should have been updating to 2 and working closely and being like, can we have the beta of 3 or what, And we've talked about that some. I think we'd fix a bug, but we weren't using your entire code as a test, which would have maybe.
And the other thing I have to say is that if I hadn't have seen it for decades, right? I mean, this has been an issue for decades with the PGI compiler, long before you bought, you bought it. And so it's like, do I have confidence that it's going to be fixed?
I mean, it's a good point. I don't have those years of experience. I see an optimism. I see it like, oh wow, they fixed this, they fixed that, but I don't know what happened before.
I mean, we started the Turbo project, and I think we racked up 4 compiler bugs.
I mean, we hit a bug as well.
It's atypical though, I guess, for us. We see like all compilers have bugs, and we see bugs and we fix them, but our Fortran compiler is not like it's not like a startup or something where it's not in use. It's in use by NASA for Fun 3D. It's in use in production. It's in use by TWC for like Graph 7, MPass 7. It's like it's working in production things. It's not like it just seems like we've struggled a lot with the codes that like your interaction has been poor. You know, that like not that
Yeah.
you've been poor, but like it hasn't worked well for you.
I think, you know, and I think this is a community that's really struggled with NVHPC. I mean, I think sometime in the past, you just stopped supporting it because it never worked. Right? And so you went on and you used Intel and you used GNU.
Yeah, and that was prior, to be clear, right, as you said, it was prior to it becoming NVHPC. That was a PGI legacy, but right, that was like PGI, supporting what John is saying, PGI was always the thorn in our side. It was, yes, all compilers had bugs, but PGI probably had about an order of magnitude more compiler bugs that we ran into.
And they would be fixed and then they'd reappear.
Yeah.
So I just to take the add to what David had mentioned. So we are right now we are working with Brian, Sherry, and others to integrate some of the codes like CESM, MPass, and URAM into our NVIDIA test suite. So that's
to test the compiler.
Yeah, to test the compiler. So whenever there is a new version being released, we'll make sure these codes are tested and they don't break. So that's what we are working as of now. So it's we started in January.
Yeah.
Well, and some of this get resolved because sounds like you said like the next one is Flang based, which assumes like the LLVM. So will like some of that help? Because it seems like some of these are just old PGI compiler problems. Do we think some of that will go away if we?
Right. I mean, that is the idea. It's moving away from from PGI Fortran that was rebranded as NV Fortran, but still the same machinery and same sort of thing.
And when will it be available?
It's available like for select people to test. For example, we could probably give it to you to test. Yeah.
We get it. Okay.
Yeah, but I don't want to get in trouble. Maybe I wasn't supposed to say that. But
I've for several years I've
floppy
heard
it's
how NVIDIA.
Yeah, you've heard it's coming, right?
For several years, I've heard that NVHP's, the Flang's going to fix it.
Yeah,
I mean, and so
I think there was a.
And so,
right. You don't believe it until you see it.
I don't believe it until I see it, and it compiles and it doesn't break the bug that was that you fixed like 3 months ago.
Right. And I can't say that it's gonna work out of the gate with your code. I mean, I'm not gonna. It's still something you gotta help. Like, is it working? If you only give us one shot and it works or not, and then you throw it away, like, I don't know, right? But it's much better. It's doing other codes.
Anyway, it's not one shot.
Well, I mean,
but anymore,
there might be, PGI and NVIDIA, maybe something has changed culturally in that interval.
Yeah.
And I would say arguably I showed a few bugs in the compiler when I was going over some of those things very fast. I feel like these are not technical problems. Well, they're technical problems, but they're also human problems. Like perhaps we haven't properly built the relationship with the compiler vendors that we should have.
Yeah.
I wonder if this is solvable.
With code, I think if somehow we never had your code to be able to run it, right? And some of the other codes that we've been pretty successful that I would say like, hey, this code builds.
Yeah.
Like Renee ran MPass all the time. So he was running internally using NV Fortran, giving bug reports as well, right? I was running Fun Overflow and being like, oh, okay, this is going on. So I think if we struggled to ever help own your code and be able to run it for us that are the engineers, not the compiler engineers, that's one thing that's helped these things go along is that like we can show the compiler engineers, here's where the bug, we're working with the customer closely.
Yeah.
And then it works better.
But I mean, so right now you have extreme vendor and compiler lock-in. There's one solution, NVHPC, right? And so using C++, if the compiler is busted, you can just switch over to a different compiler and you can submit the bug report and then you can continue on doing your own development work, right?
True. Yeah.
So I mean, I guess I brought this up because of the 2 points that John raised and also that Ren brought up. Like, I don't think it's a big deal that grad students right now are learning C++ and Python. I mean, in my experience, the only people who came into a job at NCAR knowing Fortran, where people who happen to be working on probably an NCAR code base in Fortran in a previous research project. Most people come in not knowing Fortran, and if you know any other language, it's pretty easy to pick up. But the compiler issues are bad, and so I mean it's good to hear that the Flang transition might reduce the downtime due to compiler bugs, and that it might speed
Yeah,
up
we
this
think it
process
should be-
of getting things fixed. Like
It's a more modern way to do compilers that should be a lot more fixable for any issues and also does things the right way for object oriented and handling these more complex, not just Fortran 90 type codes or something, these like more complicated
I mean,
ones.
our test-driven development can be done in an NVHPC compiler right now because NVHPC compiler doesn't support PFUI.
Yeah.
So,
Is that right?
yeah. So I mean, the whole approach of test-driven development, it's not possible with NVHPC.
Although, I mean, yes, that's an issue. On the other hand, like you don't need to be building your tests with the same compiler that you're using for production. So that's not really that's
Well, until you want to run unit tests on the GPU.
yeah.
Right.
Cheryl's got her hand up too.
So you had said that you're testing CSM1. We have alpha tags out there right now for CSM3 that are pretty stable. Would you be interested in getting, one of those, or, we've got the release coming up probably sometime this summer. So if we were to get that code to you, then you guys could be proactive in making sure that it's working. And
I'll let Renee answer right
Yeah,
now.
so, Brian, we are working with Brian on that, where Brian will be providing us with CESM code,
okay,
which first our internal compiler team will test and add that to the test suite. So that any new version release of the compiler come out, they will be first tested with CSM and make sure it doesn't.
But which version? Do you remember? ESM3 or are we on 2?
I think it's on 2, not 3.
yeah,
I can
so,
confirm.
there's a layer here that you're talking about with Bren. She's not, or they are not actively doing the development of CESM3. Some of us in the room here are actively doing development.
Yeah, so what you're saying is
Even
you
that
connect
step closer.
closer to the beta or whatever.
Right,
Yeah.
right.
I mean, yeah. What I said about CESM1 was like, we kind of we said, well, we think we are having this, what's the deal? And then we kind of compared notes and we're like, oh, we're just kind of waiting. We just basically haven't refreshed any of the stuff from you guys. So for us, it's passing compiler test, but it's actually like a 10-year-old version, or something. So that was a problem of misalignment of like, we'd like to test, against whatever you guys have. Yeah.
Yeah, we tend to have probably like an 8-year lag on the Fortran standards. So CSM1 might not have had even like CSM or Fortran 2003 code in it. Like we might have been stuck on 9095.
Right.
And like now we're starting to bring in like 2013 or 20. I can't remember. Like we're not using 2018 yet, but we're using 2013, I think.
To your point, like about, compiler bugs, I think a lot of the compiler bugs you found though were with do concurrent, right?
Yeah.
So, that's a very new thing that would be expected to like kind of have compiler bugs, right? Find another compiler that's even implementing do concurrent,
Oh,
like
I mean,
on GPU. Yeah.
GNU can't even do local variables.
So, right. So that's a very fresh thing you're trying out. And so it's kind of, that part to me makes sense that there's going to be a lot of compiler.
I mean, my expectation, it matches my expectations. I'm not like, I'm okay navigating this. I mean, I feel like, we have, as long as we have the ability to report it, as long as it's being taken seriously, and as long as NVIDIA is still willing to put resources into the problem.
We're not giving up on Fortran. And to your point too, like when it was PGI back in the day and you switched to Intel, when it was PGI, NVIDIA as a company supporting that was a much smaller, tiny company.
Yeah.
Right now, and Intel was a very well-off company that supported compilers very well.
Yeah.
Right? So
Right.
flipped.
It's
So
good to, no, I mean, I'm happy to hear
we're hiring compiler engineers.
I'm happy to, I'm very personally happy to hear what you're saying, and do come away from this hopeful that things will be improving more.
So I'm not a C++ programmer, but can I ask what bug frequency one has in most C++ compilers? Like, Is it something people ever talk about, or are they always pretty pristine things that it's just a rare event?
I've been told about that, but maybe people online could comment more directly on that. Well, do you want to, you came off mute.
I don't know if I'd say I'm a C++ expert, but I think that you could definitely find corner cases. But I think if you look at someone like C++reference.com or something like that, it's pretty widely like finding out what features are and aren't supported by a compiler is pretty easy to do. It's sort of like kept up to date by the C++ community, and just because so many people use it, not just in HPC, but just like across the board, things are pretty well hammered out. And sort of on the time scale of things, like most of the compilers you can get now support everything up through C++20, which was maybe one standard before the most recent one, which was C++23. So like I would feel pretty confident using everything in C++20 in just about any compiler worth its weight in bits. Maybe some stuff in C++23 won't work on some compilers depending on what version you have. This is sort of the table, as it sits now. So
I mean, there's like an order of magnitude larger development community.
Okay.
So they're going to catch the bugs, and because these vendors are money driven, then they're going to put the money into the satisfying 90% of their customers versus 10% of their customers.
But by the way, I have somebody from the compiler team telling us that that's not the case, right? That they're actively interested in.
Yeah, well,
in having
no, I mean, he's right. The portion of money, say on NVCC, the CUDA compiler, the not NVHPC stuff. I mean, that's where the DL is. That's where a lot of this stuff is. So of course, like there's way more compiler engineers employed in NVIDIA working on that.
Can you comment on the size of your Fortran versus C++?
Within NVHPC? Within NVHPC.
So how many people are you? How many people do you have working on C++, and how many people do you have working on Fortran?
Within the HPC compiler, I think it's probably I don't exactly know, but it's about equal or more in Fortran. I mean, that's the niche of it that it kind of has, right? Like it's the NVHPC toolkit, not the toolkit, but the NVHPC compilers is geared towards, we need to support, like you said, this lock-in. It's also like there's codes that we want to run on NVIDIA GPUs that really only work in Fortran with OpenACC, and we're going to make sure that keeps working. We're not going to give that up. So I think there's a lot of within NVHPC, there's a lot of emphasis on the Fortran side more than NVHPC on the C++ side. But within the company, of course, there's a lot of emphasis on NVCC for compiling just straight CUDA kernels in C++. Does that make sense, though? Is that what your question was?
No, I'm just wondering how much they're really investing in C++ versus Fortran.
I think the NVHPC compiler is heavily invested in Fortran, probably like 50% or more in Fortran than C++.
That's surprising.
Well, it's because that's what it really can serve, right? Like there's a lot of codes out there that use
it's reassuring, but it's also surprising.
But what I mean is there's a whole nother division that's the NVCC compiler, that's the CUDA compiler. How do we make CUDA kernels in C++?
And how big is that?
Oh, I mean, yeah, bigger, huge.
What does that mean?
I don't know how, I just know, definitely, sure, a lot more funded, yeah.
I know this has become an NVIDIA gossip session.
Well, at least.
If the transition to Flang, will that just merge all of this under one umbrella, where Fortran bugs really just be front-end bugs, and we'll actually just all be talking about LLVM? Is that the vision?
I'm not sure.
Okay, we're probably pinging you way too hard.
Yeah. I'm not sure about that.
But you heard that, right? 5x.
Well,
sure, but that's.
But I also heard that there's a little bit of comparison of apples to oranges, so I wouldn't go I'm hearing that. I think you're hearing the piece that you want to hear, not hearing the piece that you don't want to hear, John. Like he's saying that in terms of the NVHPC compiler, that there's truly is still an investment in Fortran, and that's an important thing to hear.
If we switch from Fortran to C++, we're still going to be in the HPC world, and we're still going to be using.
Right. If you want to switch to CUDA, you could have that 5x more developers if you pure CUDA. But if you want to just switch you know, to something. So what are your, yeah, I don't.
Well, anyway,
It's like, yeah,
I don't mean to beat up on him.
No, it's okay.
Because I feel like I'm doing it. But there is basically, you know, a level of frustration. Multiple projects with the Fortran level of support.
Yeah.
Can I ask another C++ community question? Lalo and Michael have both been helpful.
Yeah.
How many, oh, okay. Like, if one was talking C++, is there like an order of magnitude more compilers out there to talk about? And if so, like, how many are like you said, how many target the sort of systems that we care about? I could ask ChatGPT.
I guess there's a lot of,
Go
ahead.
No, I don't know if I know necessarily say an order of magnitude more compilers. I think it depends on what you're doing and where you want to run. So like, for instance, and maybe this is mostly with my experience before joining NCAR was we'd run a lot on DOE systems. And I mean, obviously they're pretty heavily invested in running C++ code. So the compiler support on the machines was always pretty much there to where, you know, you would use whatever your system default compiler was. But if you were a developer working on your laptop, you can get pretty much the same version and go back and forth. So I'd say that, but I mean, yeah, I mean, GCC's out there, Clang is big. NVHPC, obviously, if you're using you know, stuff that gets compiled down to, you know, CUDA or something that targets CUDA. So I mean, so I'd say those are probably the big three in the HPC world, just like on the Fortran side.
I mean, but even GCC, like, I mean, as much as I'm a fan of it, it doesn't really target what we need. You know, so I mean, if we're talking C++ on HPC, we talking NVHPC?
No, that's where I think the misconception is that like, basically if you want, let's say you're going to write your code in CUDA, raw CUDA, and you're going to use C++, because that's what you need to use real raw CUDA. You would call NVCC, and that's NVIDIA's CUDA compiler, but it is a compiler for compiling the device code, and it uses a host compiler, and it'll use whichever one you point it to. You could point it to G++, you could point it to Intel, you could point it to Clang.
I see.
So all those work, and probably all your complicated C++ stuff sort of is handled by, does that compiler work with it anyway? But then inside the kernel, if you have some really complicated stuff inside what you want to make a CUDA kernel, that might not work. But that might go back to, well, CUDA is this extension, and we say we don't support this inheritance within a kernel and blah 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 or something, right? So
even then though, it's like
C.
that's not the part of C++ that interests me. It's the solvers that interest me. It's the kernels, right? Like that's the part we should be most invested in. All the other stuff around it has always been decoration.
Right.
I would say that on that end, like for instance, right now in the Turbo projects where we're using AMRX, like AMRX is our middle layer, and then on the bottom of that, they're going to target, you know, like x86, or they could be generating, you know, PTX run NVIDIA or stuff around AMD GPUs, or they can even run on Intel GPUs. We haven't tried it, but like in our CI test right now, we have our C++ AMRX like mini app code essentially that's compiled in, and we use basically AMRX with the backend compiler that is like GCC, Clang, Intel, and NVHPC. And so, like you're saying, we kind of are focused on the code and don't really care about the compiler. And like we have these sort of 4 options, and we should get the same answer with all of them. Maybe we get like different performance or like hardware targets and that kind of stuff. But like as the application developer, you're worried about what's the code doing, not what's the compiler doing. Maybe if you're a performance engineer, you care the other way around. But you know, for right now when we're in development mode, it's just our CI has multiple tests and they all use different compilers and they all get the same answer. And that's fine.
I believe we're using the CUDA compiler for it when we compile for the GPU. So we're getting advantage of this.
Yeah, I was trying to avoid that conversation somewhat because AMRX and same with Cocos, it's easy to get confused a little bit and think, well, I'm using the CUDA backend for these, so it's like as good as CUDA. As good as sort of writing raw CUDA, as if I wrote CUDA, and there's some hiddenness that the abstraction layer puts in there that doesn't allow the compiler to make the same optimizations it would if you wrote your same thing in CUDA. Okay, so just the fact that it uses the CUDA back end is not gonna give you the same exact performance. Not even like, oh, just 5%. I mean, it can be significantly different.
One note on that point too is that, like, so for instance with AMRX, and I think in Cocos you got the same option, is like we're not that far because the turbo project still sort of, we're rapidly prototyping things, so we haven't hit the performance aspect of it yet, where we're just like rewriting kernels for performance optimization. But one of the nice things is that, like, they do give you the opportunity to say that we profile our code, we realize one of our kernels is like the hot kernel that is taking up most of our runtime, and we just want to rewrite that one kernel in CUDA and leave everything else in the high level, AMRX program model. That we do have that option, I think. And I mean, I know less about Cocos, but I believe they do the same thing. So we might end up doing that, where we drop down for specific key performance kernels and we write just say a few in CUDA and everything else stays high level. But we don't know if we're gonna do that yet. Like I said, it's.
I've ported codes for like 20 years to the GPU, or maybe not quite that much, but that's what you should do. Like you want to work with something that has that option, because there's going to be maybe one hot kernel is worth doing that for to get 2 or 3x on that kernel, and it's like 40% of your runtime. So, we're all for using like portability that really eases the burden of maintaining. But if you feel like you have to write this one code that does it everywhere, always, you might limit yourself to just like, could you just maintain 2 versions of this kernel for 2 different vendors that is really optimized and works really well? Yeah.
Okay, so on that note, I think we're 10 minutes past the end time. So thank you everyone for coming. The plan for tomorrow is just to work on project